In this demo, we are going to display the capabilities of the digital I/O module to generate digital vector patterns at up to 100 MHz vector rate. In fact, NF1208 is able to generate digital vectors at any frequency up to 100 MHz. We know that for functional test of semiconductor devices, test vector input is a key component. For example, we may want to program the different edges within a cycle of a digital pattern data. And also, sometimes different devices require different kind of data format. For example, RZ format means return to 0 within each cycle, and R1 format, which means the digital input data must return to 1 before each cycle ends. NF1208 digital I/O module addresses all these requirements. Let's take a look at its digital pin capabilities. Firstly, it is industry's first PXI trio size 100 MHz pin electronics digital I/O module. It has a digital pattern generator and analyzer with up to 100 MHz vector rate at any frequency. This module has 8 channels with per channel per cycle bidirectional control capability. It also features AMAC generation vector memory and a separate AMAC acquisition vector memory per channel. This module supports complete data format, for example NZ, NRZ, R1, etc. per channel. Still IEEE 1450-1999 compatible events for each of the 4 programmable edges within a cycle are supported as well. We are able to do time set change on the fly for this module. Besides, this module is able to do real-time onboard hardware comparison for DUT data that is being captured. It has advanced trigger and a pattern sequencing capability, and if you need more channels, it supports multiple module synchronization. NF1208 digital I/O module works with National Instruments PXI-based FlexRail FPGA module. On the diagram you can see NI FlexRail FPGA module is the PXI module for the PXI platform, and NF1208 is a custom adapter module or terminal block that is mounted on the front of the FPGA module. Both hardware works hand in hand together to deliver the digital pin features. Now let's move on to the actual demo to see the capability of this module to generate digital vectors at any frequency. For the demo of showing the digital I/O capability of this module, we are going to use channel 2 and channel 3 this module. These 2 cables of the module actually connect to the oscilloscope so that we can see the output signal on the oscilloscope screen to verify that the module is indeed doing what we asked it to do. In this demo, we are going to show you the capability of NF1208 digital I/O module to generate digital patterns at any frequency. The first part of the demo, I'm going to program the module to generate 100 MHz vector frequency. So I key in 100 MHz on the screen. I click OK button. The next thing I do is to check this box continuously to program the module to generate the digital pattern 10101 continuously. So I check this box, I click the sync button. Now the digital I/O module has been programmed to generate vector data 10101 at a vector frequency of 100 MHz. Now let's look at the actual screen output on the oscilloscope to verify the I/O module is indeed generating frequency at 100 MHz. This screen displays the 2 channels of vector data of 100 MHz that we are generating from the digital I/O module. Remember that we are generating vector data of 10101, which means on the oscilloscope the actual signal frequency measure will be half of the vector rate, which is 50 MHz. Now let's zoom on to the measurement data to check that it's indeed generating 50 MHz signal at 100 MHz vector rate. As you can see from the measurement data on the oscilloscope, the signal frequency is 50 MHz, which is half of the vector frequency for the vector data that we are generating, 10101. The positive pulse width, which represents vector data 1, and the negative pulse width, which represents the vector data 0, both of which the period is 10 nanoseconds, which corresponds to the 100 MHz vector frequency. Now let's move on to the second part of the demo, where I'm going to show you how to use NF1208 digital I/O module to generate another frequency. Let's stop the current 100 MHz frequency generation. I clear the checkbox, and the digital I/O module frequency generation will stop. Let's say I want to generate another vector signal at 82 MHz. I just key in 82 MHz. I click OK. I check this box. Then I click bursting button again. Now the digital I/O module has been programmed to generate a vector signal at 82 MHz frequency. Note that the vector data being generated is 10101. This screen shows the actual output of the signal on the oscilloscope. We can see that there are two channels of digital pattern data being displayed, channel 2 and channel 3. They are shown as the two curves on the screen. Now let's zoom into the measurement data to look at the frequency and the positive and the negative pulse width of the signal. Note that previously in the software we have programmed it to generate 82 MHz digital pattern. Remember that we are generating a digital vector pattern at 82 MHz vector frequency, and that the vector data that's been generated is 10101. Therefore, on the oscilloscope, the signal frequency that's being measured will actually be 41 MHz, which is half of the vector frequency that we are generating. Similarly, if you look at positive pulse width, which represents a logic 1 in our vector data, or negative pulse width, which represents logic 0 in our vector data, both of them show 12.19 nanoseconds, which is the period for our 82 MHz vector signal.